Alright, so today we're looking at tangents, and I think my numbering is a little different than yours. Do you have postulate 8.10? Okay, my number is going to be one off, so this is a 10, this for you guys you have 11. And remember a tangent, if I gave you those definitions a few classes back, a tangent line is a line that touches the outer rim of the circle once, only once, right? And the point where it touches we call the point of tangency. We're going to use a postulate that I listed here, and a postulate is something that you accept to be true but you can't prove it. It's kind of the building blocks before it proves. So here's a postulate that I'm going to be using, and it just says at any given point on a circle you can only have one tangent line. There's only one unique, and so that's something we can't prove, but we're just going to say we're going to work with that and build upon that. Okay. So theorem 8.11 says that if a line is perpendicular to a radius at a point on the circle, then that line is going to be tangent to the circle. Okay. So we're given a radius, we're given a line, and we know they're perpendicular at that particular point. And so why would it be tangent? In other words, why would that be the only point that could touch the circle? Well, if I pick any other point on that line, what can you tell me about it? Why can't any other point on that line be on the circle? If this is perpendicular, what does perpendicular have to do with that idea? Do you remember when we talked about shortest distance from a point to a line is always perpendicular? So because OP here is perpendicular to our line, that's the shortest that distance can be. So if you pick another point, the distance from O to that point has to be longer than the distance from O to P. Make sense? So that point's got to be outside the circle because it's longer than the radius. And so that's enough evidence. It's kind of a weird proof and more of an explanation kind of proof, but that's the reasoning behind this proof that says, hey, if we're perpendicular to one point, it's got to be tangent. Okay. Not so important that you know that proof, but it's really important that you know that theorem. Okay. The second theorem right after it, which is 8.12 for you guys, is the converse of that, which says that, okay, let's say we start with a tangent to a circle, so a line that hits it at one point, then it's got to be perpendicular to the radius. Okay, so let's say this line M here is tangent to our circle, and the point of tangency is at point P. And here I'm going to just verbally argue using proof by contradiction. So let's say that angle there with the radius and that line, let's say it's not 90 degrees. Okay, let's say it's something else. Say it ends up being here 82 degrees, just for fun. Okay, so then there must be some other line that goes through that point. We'll call it line B here, where it's perpendicular to point P, or PO, the radius, right? So if line M is not perpendicular, then there's got to be another line that goes through that point that's perpendicular. So let's say that's line B. Well, if line B is perpendicular, so if we have perpendicular here to the radius, then we go back to theorem 8.11. What does that say about line B? That would mean that line B would have to be tangent. But we already have line M as tangent, don't we? And what does the postulate say? You can only have one tangent. And so that's a contradiction, and therefore we know it can't be 82 degrees or anything else. It's got to be 90 degrees. Okay, so that's a proof by contradiction. Again, you don't have to know that proof, but you do have to know what the result is, that if you have a tangent to a circle, then it's perpendicular at that point of tangency on the circle. All right, so next one, theorem 8.13. Here's the parts where I want you to understand the proving now, okay? If you have tangent segments, so drawn to a circle from one external point, then those tangent segments are congruent. So here we have point P, our external point, and we have these rays that are tangent to the circle. Here one at point Q, the other one is tangent at point R. Those are our points of tangency. So the tangent segments would be PQ and PR. And so saying, hey, if we have this scenario, the distance from P to Q has to be the same distance from P to R. Well, how can we prove that? I'll give you a hint. It has to do with triangles. So let's connect O to P, O to Q, and O to R. And let's try to argue that those two triangles are congruent. Because if we can, then we can easily get that PQ is congruent to PR. Okay. So why would those two triangles have to be congruent? What's congruent? What are the congruent parts that we know already? Yeah. QO and RO have to be congruent. Why? They're both radii of the circle. Perfect. What's another thing? Yeah. It should be 811 or 812. Which one? 812 says if you have a tangent, then it's perpendicular, right? So we know they're both right angles. Perfect. And so why are the triangles? That's enough right there to say that the triangles are congruent. By what? Hypotenuse leg. So we have congruent triangles by hypotenuse leg, and I'll write this down in a second. So then because the triangles are congruent, we get our result. Okay, so let's write this proof down. So our first statement is the given that PQ and PR are tangent to circle O. And that's given. And because it's tangent, what that given gives us is the 90 degrees, right? Or the perpendicular. So we could say that the measure, or we could just say angle PQO and angle PRO are right angles. And how do we know that? Well, we said the theorem 8.12 tells us that they're perpendicular, and perpendicular means right angles, right? So we're using the theorem, and then we're also saying using the definition of perpendicular. So then we also made a couple other observations. We said that OQ is congruent to OR because they're both radii, or those are points on the circle, and by definition of a circle, every point on the circle is the same distance from the center. So I'm going to just put the definition of a circle. And then we said OP is congruent to itself. And that is the reflexive property of congruence. And those 4 steps now lead us to congruent triangles. That triangle PQO is congruent to triangle PRO by hypotenuse leg congruence. Because our hypotenuse, which one's our hypotenuse in this picture? PO is the hypotenuse. Hypotenuse is always across from the 90 degrees. And then the 2 radii are the legs, and they're both right triangles. And then lastly, because they're congruent triangles, we can say that corresponding parts, in particular, PQ and PR, have to be congruent to each other. So CP, CTC. Okay. What else is congruent in this picture? What are some of the other parts that we didn't mention? Yeah. Oh, I did. Sorry, this should be PR. Okay. Okay, so we could also have proved that this angle is congruent to this angle, right? It is. It's an angle bisect. So OP is an angle bisector of this angle, the QPR, and it's also an angle bisector of QOR. And that, if you look at the next 2 corollaries, that's what they state. So corollary 8.14 says, if you got this picture here, okay? So if 2 tangents are drawn to a circle from an external point, then the line segment from the center of the circle to the external point bisects the angles formed by the tangents. So that those 2 angles have to be congruent. And we just kind of proved that, right? I'm going to make you write that proof, but it's pretty much copying down what we just did. Okay. And then the other one that we stated, if you look at corollary 8.15, says that if 2 tangents are drawn to a circle from an external point, then the line segment from the center of the circle to that point bisects the angle whose vertex is the center of the circle and whose rays are the 2 radii. So if you look at the picture again, it's these 2 angles are congruent, the QOP and the ROP, and same proof as what we did as well. So these are just extra results we get from that proof and things that I want you to know. So part of the homework is for you to just write those proofs for those 2 corollaries. Okay. All right. So to summarize some of the things we were saying, a tangent line intersects a circle at exactly how many points? Exactly 1 point. That's the definition, or that's part of the definition of a tangent. And we call that point the point of tangency. Okay? A line is tangent to a circle if and only if it is perpendicular to a a radius drawn to the point of tangency. Okay, and so that's the key theorem right there that that we're using. So let's now apply some of this stuff. We're going to skip around a little bit. We're going to look at a few problems that we're going to apply this to. So number 1 and number 2 here asks to determine if AB is tangent to the circle P. So we don't know if it's tangent or not. We're asked to just figure out if it is. And so let's look at number 2. How would I know? How would I know if AB were a tangent segment to that circle? Or if it were a tangent segment, what would be true? We would have a right angle here. And so it would make that triangle a right triangle. And if it's a right triangle, then the Pythagorean theorem would work. Now, if it were not tangent, then that would not be a right angle, and the Pythagorean theorem wouldn't work. So the test here is let's try out the Pythagorean theorem and see if it works or not. Because if it works, then we got tangency. If it doesn't work, then we don't. So the Pythagorean theorem, how would I set it up? What would I write? 14 squared plus what? 11 squared equals 5 squared? Now careful, is this length really 5? It's not. We know the distance from P to the circle is what? 11. So it's got to be 16. So careful with the picture. Okay? So it's really 16 squared. Okay. So we don't know if they're equal, so actually I'm going to take that equal sign off, and we're just going to check both sides, see if they are actually equal. So what is 14 squared? Anybody have that? 196? And 11 squared? And what's 196 plus 121? 317. Okay. Is that going to be the same as 16 squared? Yeah, you know, if you actually multiply 6 times 6, so you're not gonna get the 7. But what is 16 times 16? You got it? 296? 56. Are you sure? So are they equal though? No. So is it tangent? No, because that's not a right angle, and so they are not tangent. So AB is not tangent to circle P. Okay. All right. Then from here on out, we're going to be told that we're working with a tangent. So here, numbers 3 through 8, we're told that JK is tangent to the circle, and we want to find X. So let's take a look at number 5. Okay, X is just this piece here. Okay, so if I want to find X, what do I have to do? Okay, use Pythagorean theorem to try to figure out. So what would this full length be? If this is 10, right, the radius is 10, so it'd be x plus 10 here. Okay, so if we set this up, we get 24 squared plus 10 squared is equal to x plus 10 squared. Right? Now, 24 times 24, 576. 10 times 10, 100. And here we're going to have to figure out what x plus 10 times x plus 10 is. And so we get 676 is equal to x squared plus 10x plus 10x plus 100. And then I'm going to subtract. So if you have, well, I'll do this one more line. So 676 is x squared plus 20x plus 100. And subtract 676 from both sides. You get negative 576, which, so now this is quadratic, and we're going to, remember when we were solving this before, way back in unit 2? We had to try to factor it. So we were looking for two numbers that multiply to negative 576 and add to positive 20. Now that's a big number, but notice 576 is 24 times 24, right? So I'm going to break that down. So I'm going to use a space up here. So 576 is 24 times 24. Break it down further. 24 is 4 times 6. 2 times 2. 2 times 3. So the prime factorization. So if we break down 576, how many 2's do we have? 6? And we have 1, 2, 3's? 2 3's? Okay. So there's a prime factorization. So those are the numbers that make 576 when you multiply them together. We need to split them up somehow so that when we subtract, we need to come up with two numbers that when we subtract, we get 20. So it's a little bit of a guess and check game here, right? So we could try, let's see, what if we do these 2's here and these right here? What do we get? 2 times 2 times 2 times 2 times 2 is what? 32. And 3 times 3 times 2 is 18. And if we subtract those, what do we get? Do we get 20? No. So let's try something else. I'm going to give you a second. Try it out. Try to find out what it's going to be. So if we take 4 2's and this right here, so we have 16 and 36. We subtract those, we get 20. Okay. So this is gonna. So we want the 16 to be negative and the 36 to be positive. So when we multiply it together, we get a negative answer, but when we add it, we get the positive 20. So this is going to factor to x minus 16 times x plus 36. And so we set our factors equal to 0. Solve. And get 16 or negative 36. Which one do you think x is? Probably the positive one because we're talking distance here, and so we throw out the negative answer and keep the positive one. Now this is an exception here. Most of the problems are not this challenging, okay? I wanted to show you a challenging one. Yeah. There you go. There you go. Okay. If you look a little bit further, we see the more tangent line properties. This is one of the corollaries that that we proved. Okay. Or actually one of the theorems we proved, and the corollaries that you're going to work with off of that. And sometimes you'll see a picture like we skip down to number 13 here. Sorry. We can use that a few times. So because this is tangent here, we got 16, and it's going to be congruent to this one. So we get both are 16. Then we can use it again. These are tangent, so they're both going to be congruent, and so we know that this is 11. And we could do it one more time over here and get 9.5. So if you have to find the perimeter, you can add all those around, okay? I'm going to stop there.